Welcome back to CS270. We're going to talk today about synchronization. This is the last set of videos for the class. So we're following up on concurrent programming that you saw in the last set of videos. And in those videos, I mentioned that when you're doing threaded programming, so writing a program that has multiple threads of execution running within the same process, there are lots of complications and difficulties that make it easy to write a program that has subtle bugs. So we'll talk about some of those and about what you can do to avoid them. Um, so the problem comes down to shared variables. If two variables or two pieces of data are, or sorry, one variable or one piece of data is shared among multiple threads in the same process, we have to be really careful about how we access them. So that raises the question, which variables are shared? Um, well, by definition, a variable is shared if multiple threads reference some instance of that variable. I say instance of the variable because for local variables, there could be multiple instances. If a function is recursive, then there will be multiple instances of that variable at the same time. If it's not recursive, then every time it's called, it will be a different instance of the variable. Um, so if we want to use that definition, we have to look into a few things. How does memory work in threads? How are variables mapped into memory? And how could threads reference variables of each of those kinds? Now, we saw a little bit about the second question already, in that we know that local variables are stored on the stack, global variables are stored in the data section of the program. Static variables or static local variables, so a variable inside a function that's declared static, are really just local variable or global variables with a limited scope, so they're also stored in the data section. So let's take a look in some more detail. So the conceptual model of threads is that you have, which we saw in the concurrency videos, is that you have multiple threads running within the context of a single process. Each thread has its own stack, its own stack pointer, its own program counter or instruction pointer, its own copy of the registers, and each thread has its own thread ID number. Um, Everything else is shared among all the threads, so that includes the code. The threads have their own instruction pointers, so they might be executing and probably are executing different code at the same time, but it's still the same code. If I'm calling a function from two different threads, they're going to be executing possibly the same code at the same time. Data, so this is the data segment of the process. Global variables, and we'll see also static local variables. The heap, things that you allocate with malloc, are also shared. Shared libraries are by definition shared among multiple processes, but also shared among the different threads within the same process. Now, of these things, the code and the shared libraries are read-only, so we don't necessarily have to worry about those so much. But the data and the heap are read-write, and that's where we can really run into problems. And besides all of those things in memory, things like open files and signal handlers and so on are also shared among all the threads. So that's the conceptual model, but in practice, it's not necessarily always true. The register values really are separate. They really are protected from other threads. They are within that thread, and when we switch to another thread, they're saved and loaded. But the stack is actually in memory, that thing that's shared. Each thread does have its own stack, but all those different stacks are in the same memory space, and a thread could refer to the stack of another thread. The way this would usually happen is if your thread gets passed or somehow gets access to a pointer to a local variable in another thread, and that can be a real problem. And the fact that that can happen is a common source of errors in multi-threaded programs. So let's take a look at an example program. So here we have, and this is in the Lecture 18 code as sharing.c. I'm not going to run this one on the VM, but we'll see some things running on the VM in a little bit. So here in main, I have an array of strings, so messages 1 and 2. So these are local variables. They are stored on the stack. I have a global pointer. So this is a char star star. So a pointer to a character, which really here means it's going to be a pointer, as we can see from how it's assigned. It's going to be a pointer to this array of pointers to character arrays, null terminated character arrays. So we'll assign the global pointer to point to that. The reason we're using a global variable here is so that all the threads will have access to it. And then we'll go in a loop, just 2 iterations, create a peer thread in each of those iterations, and then we'll exit the program once that's done. And if you look at the man page for pthread exit, we see that actually it only terminates the calling thread. So we're not terminating the whole program there. It's okay if the main thread exits here and the other threads aren't finished. They will keep running until they finish. The other threads are running this function. So over here on the right-hand side, it gets a copy of this number, I. So notice we're taking this number, casting it to a void star. This isn't taking a pointer to the local variable I. This is making a pointer whose address is 1 or is 2. Now we wouldn't be allowed to use that pointer, but we're actually just going to cast it right back into a long. This is actually technically undefined behavior in C++ at least, but on most compilers and on GCC it does work. So even though it's supposed to be a pointer, really we're passing a number. So we'll convert that back to a number. We have a static variable here. So this is a local variable in the sense of scope. It's only accessible inside this function, but there's just one instance of it throughout the entire lifetime of the program. Meaning this is really like a global variable, meaning it's shared among all the threads. Inside the thread, we'll print the ID, that thing that we were passed in, so 0 or 1. We'll pass print rather the message at that index. So whichever one is 0 will say hello from foo, whichever one is 1 will say hello from bar, and we'll also print the count, which we are incrementing here. And then we return null, returning from the thread procedure that we called with pthread create terminates that thread. We don't have to call pthread exit in that situation. So all of these threads are sharing some things and not sharing other things. My ID here is a local variable within the thread process, or within the thread function. So there's going to be one copy of that for each thread. They don't share their stacks. Count here is a static local variable, meaning it is shared among all of these threads. And this pointer is a global variable, but it's pointing to something in the main thread stack. So even though each thread has its own copy of the stack or has its own stack, they can still, by following pointers that were assigned in such a way, refer to things in the main thread stack. So let's try running that. So this is the lecture 18 code directory. We'll run sharing, and we see we get hello from foo, hello from bar, count as 1 and 2. So everything looks like it works here. It turns out there are actually some problems here. And we are not likely to see them in such a small program because chances are whichever thread executes first will have a chance to finish everything that it's doing before the next thread starts. So they are likely not to actually be running concurrently. If we want to have them running concurrently, if we put a little bit of a delay in here somewhere or so on, we could end up with that situation. And we'll see in another program later on how some of how that can cause problems. So again, global variables, which are variables not inside a function, are shared. There's just one copy of that in the entire virtual memory, so all the threads have the same global variable. A local variable, one defined inside a function, without static, each thread will have its own stack, and that stack will have its own copy of that local variable if that function's being called. And remember, we can call a function multiple times, so there might, over the course of time, be multiple instances of the same local variable. Or if the function's recursive, even at the same time. One for the function that was called, one for the copy of itself or the instance of itself that it called, and so on until the recursion terminates. And local static variables defined inside or declared inside a function using the static attribute are like global variables. There will be exactly one instance of each of them. So as we said, pointer here is a global. These things are local variables. There's just one instance because they're local variables in main and only one copy of main is executed. This variable, my ID over here, is also a local variable, but there are two instances of it because there are two different threads running this function, potentially at the same time. And count here is a static variable. There's just one instance of it. So it's stored in the data section, just like the global variables. And we can look at which variables are shared, which are referenced from different places. So a variable is shared if multiple threads reference the same instances of it. So the pointer is shared. It's referenced by the main thread. It's also referenced by thread 0 and thread 1. They explicitly refer to the pointer. The count variable is it doesn't appear in the main thread. It's a shared, or it's a static local variable inside the thread process. But there is just one instance of it because it's static, so that same thing is referred to in thread 0 and thread 1. This I variable in main is not shared because no one else refers to it. Yes, we're passing it converted to a pointer into this function, but that really is a copy of the variable. It's when we call the function, that's going to be put in the appropriate register for that argument, and it won't be a reference to the variable on the stack. Now, if we were doing C++ and this was called by reference, then it would be shared. Messages in main, even though it's a local variable, so it can only be referenced by that name inside of main, it is shared, in fact, because we make that global pointer point to it. So all the threads can gain and do gain access to it when they dereference the pointer here. And then my ID in thread 0, my ID in thread 1, those are local variables, not static, so they're not shared. Those are two different instances of a variable, and it's a local variable, so they are independent. So we would say here that pointer, count, and messages are shared. I and my ID are not shared. Okay, so shared variables are useful. We can do something like we just saw and have this program print out hello from two different threads and print the same count, but there's a possibility of synchronization errors. So let's take a look at another program. And here, I am going to switch to the virtual machine. So we're looking at badcount.c. Okay, so here I have a global variable that's going to be shared. I'm declaring it as volatile here. If I don't make it volatile, then we might not see the problem, not because there isn't a problem, but because the compiler will optimize so much away that that the problem happens to no longer occur. Volatile means when something is referring to this variable, it should reload the variable for memory each time. Normally, if I were to have a variable, even a global variable that I'm using multiple times within the same function, the compiler, in order to do whatever it's going to do with that variable, probably has to load it into a register anyway. And if I refer to it within the same function by name again, chances are the compiler is not going to load it from memory again, but is rather just going to use that same value in the register under the assumption that, well, it's not going to change unless there's code that explicitly changes it. Volatile tells the compiler not to do that. This is useful if you have variables that can be changed by other threads, for example, or by a signal handler or by memory mapped hardware even. All right, so this variable, we've made it volatile just because in this particular case, it helps make the problem occur more often. Synchronization errors tend to be non-deterministic, and very often you'll only actually get the problem one time in 1,000, or one time in 10,000, or one time in 1,000,000. And if that happens, you might think your program works, and most of the time it does, but sometimes it doesn't. And a program that works most of the time is probably, in most situations, worse than one that only works half the time or doesn't work at all, because you're inclined to believe that it's good, and then when it's not good, that's completely unexpected and very hard to trace down and debug. So in main here, where we take a parameter for the number of iterations, we create two threads. We pass the number of iterations in. Notice here we are passing a pointer to a variable defined in main, a local variable in main. So this initers variable is going to be shared. We're not going to write to it though, so it will be okay. This isn't the source of our bug. And then we'll start those two threads. We'll see what the threads do in a minute. We'll join to wait for those threads to finish. The threads are going to be modifying this global variable count, and if the value of count isn't 2 times the number of iterations, we'll print an error message. Otherwise, we'll say it's okay. In the thread, we have a local variable I. We also have this variable initers, which we got from main. And then we'll just run in a loop for initers times increment count, and we'll return. So it seems like, well, if thread 1 is going to be, or thread 0 is going to be incrementing this variable, let's say 10,000 times, and thread 1 is going to be incrementing the variable 10,000 times, it gets incremented 10,000 times, so it should be 20,000, which is what we're checking for. But let's see what actually happens. Let me run it with 10,000 iterations, and it was only apparently incremented 15,000 times, not 20,000 times. If I run it again, that time it happened to work 20,000 times. 20,000, 20,000. Let me try a bigger number, 100,000. Okay, now we see, oh, we only incremented it 117,000 times, not 200,000. And if I run it again, it happens to work that time, then it doesn't work. So you can see it's very non-deterministic what happens. Well, let's see what the problem is. So if you take a look at the assembly code that you get from compiling the thread function, you'll see we have something like this. We load a variable. We compare it to. So this is for just this loop. We load our variable. We test to see whether it's 0. If it's not 0, if it is 0, we go to L2. We move 0 into EAX. EAX will be our counter I. So this RCX here is our initters. We'll load that count variable, which is a global variable, into RDX. We'll add 1 to RDX. Then we'll move our RDX back into that variable. If we hadn't made that global variable volatile, then this would probably all be just a single incr instruction. But by making it volatile, we're saying that every time we load it, every time we store it, we should actually go out to memory to do that, which will, at least in this case, make the compiler not optimize that down to a single increment instruction. We add 1 to our RAX. We check whether that's equal to RCX, so whether we've reached initters. If not, we repeat. Otherwise, we come down here to L2 and finish up the thread. We would be returning, and that would return into something that calls pthread exit, for example. So this section here, this is where our problem is. So I'm going to refer to these parts as the head, a load, that's where we load the global variable into a register, update, we're updating the register, and store, we're storing the register back into the local variable. And then this part at the end as the tail. So when we have concurrent execution, these two threads running at the same time, any consistent interleaving is possible as long as the threads as long as the things that thread 1 runs are in the right order: head, load, update, store, and then finally the tail. And the ones in thread 2 are in order: the head, load, update, store, and then the tail. As long as that's the case, things will work kind of the way we expect. But they could be in any order relative to each other. There's no synchronization between thread 1 and thread 2. So in this case, there is some concurrency. Thread 1 is running from here down to here. Thread 2 is running from here to here. They do overlap in time. But what could be really bad is if the load for thread 1, the load for thread 2 happened, or let's say the load for thread 1 happened in between the load for thread 2 and the update for thread 2. So let's see a little bit about that. So here is an example of an ordering that is possible. For each thread, thread 1, we have head, load, update, store, tail. For thread 2, we have head, load, update, store, tail in the right order. But now watch what happens when these are executing interleaved like this. So RDX here is going to be the value of this local register. And we have 2 of those because we have 2 different threads. They have their own copies of the register. So this is the register that we load the value from count into, that we increment, and that we store back into the count. We only have 1 instance of count, though. It's shared. So in the head for thread 1, the count is 0. Then we load that into RDX. We increment it. We have the value 1. And now, let's say thread 2 gets a chance to run, which is entirely possible. So thread 2 will run. It will load, it will, in the head, not do anything with those variables. Then load the count into a register. Count hasn't been incremented yet. We haven't stored the value back into count in thread 1. So thread 2 will get the value 0. And now thread 1 gets a chance to run. So thread 1 will store that value back into count, then execute the tail if this was the last iteration. So let's say we have only one iteration here. And now thread 2, because the tail is the end of thread 1, thread 2 gets a chance to run again. Well, in thread 2, it just loaded the value 0 into its copy of RDX. It will increment that, giving the value 1, store that back in the count, storing the value 1, and then that thread finishes. So notice we did 2 increments, but we were incrementing 2 copies of 0 because the threads both loaded that variable before the first thread was able to store its value back. So we have a problem. We have these 2 threads interacting with each other in a bad way. We would hope for this result, where the value of that count variable ends up being 2, but that's not what happened. Here's another possible ordering. And again, the same thing. We're going to load the value in thread 1, then thread 2 runs, it loads that value 0, thread 2 stores the value 1, then thread 1 gets a chance to run again, increments, stores the value 1, and we have the same problem. So one way we can analyze this is with a process graph. So we'll take a look at that in the next video.